There it goes. Well, welcome everyone to our COINFLIPS seminar. Today we have with us Dr. Sarbajit Banerjee, who is located at the Texas A&M University. Today his talk is titled Towards an Expanded Palette of Materials and Mechanisms for Neuromorphic Computing. Dr. Banerjee is the current Associate Director of the Reconfigurable Electronic Materials Inspired by Nonlinear Neuron Dynamics, EFRC. Dr. Banerjee completed his PhD at Stony Brook University and recently received a NASA Innovative Advanced Concepts Fellowship Award. With that, Sarbajit, I'm going to hand it over to you. I'm looking forward to your talk.
All right. Thank you, Darby. I am really happy to come talk to you all about some of the work that is done in Remind and also in my research group. So Remind has existed for less than a year, but we had a lot of fun getting started. Okay, so this is my research group. What I'm going to tell you today about is really understanding how to design materials for neuromorphic computing. I think this is COINFLIPS is an eclectic group of a lot of folks that do very interesting things across the entire spectrum, and my research group is more focused on mechanisms and really understanding the atomistic basis for ideas that could turn into vectors for neuromorphic computing. And we work very closely with folks like Stan Williams and Joshua Yang and Suhas Kumar and Alec Taylin at Sandia to build devices, systems, and so on and so forth. So Remind has the EFRC that we are a part of, is led by Texas A&M, and as I mentioned, has Sandia as an important part of it, Lawrence Berkeley National Lab, and NREL. And what we're trying to do in Remind, it's very much an Office of Science project. So we're interested in understanding the foundational scientific basis for these massively reconfigurable computing architectures. So understanding what sort of intrinsic material properties underpins neuronal and synaptic function. And a lot of this involves working backwards, right? Doing inverse design from understanding neuronal synaptic properties to how materials couple with fields within devices, and then breaking that down into material properties. And so a lot of what one sees in neuromorphic computing is not necessarily just an intrinsic material property, but also its coupling with fields, also its transformations. Our core idea is that if you've got the right sort of material transformation, and if you've been able to design it correctly, that saves you a lot of heartburn in the long run, because you can really work on fundamental transformations that are low entropy and that have very little that can give you a lot of conductance, contrast, and such for relatively small lattice transformations. So this is our research plan. We're trying to really be focused on fundamental mechanisms and to come up with design principles for molecular material building blocks for neuromorphic computing. A lot of this has been a lot of sort of materials discovery for neuromorphic computing has been somewhat empirical, and we're trying to codify some intrinsic design rules and to understand how one could do better. And preaching to the choir here a bit, I don't think y'all need a whole lot of explanation for why we should care about neuromorphic computing and better materials for neuromorphic computing. Of course, I know I follow Brad on Twitter, and he often talks about the huge energy costs of AI and the big sort of tsunami of data that is coming. My NREL colleagues think I have a like natural disaster analogies a bit too much, but yeah. So, but we've got a big tsunami of data coming, and I think y'all all understand that general purpose computing is hitting a wall. A lot of times AI algorithms are very poorly matched with general purpose hardware. And really, if you sort of dial down, this all comes down to fundamental limits of silicon, right? And sort of how what can you do with silicon, or that to make it look like a neuron or synapse is fairly limited. And so these are fundamentally materials problems, chemical problems that can be resolved with better materials design, although that brings with it its own set of issues. And industrial product development cycles often don't really leave a lot of work for foundational research. There's a lot of, again, empirical material selection and ad hoc designs, and we're trying to get past that by really dialing down and identifying some design principles. And this is a case that we always make, that even though a lot of this was started here, and lots of amazing work across neuromorphic computing, our U.S. funding is now, U.S. contributions to the field are steadily declining, right? I like this quote from Stan Williams, our director at Remind: "The end of Moore's Law could be the best thing that has happened to computing since the beginning of Moore's Law," right? So this is, I think, something that kind of inspires us. So the gaps that Remind is really trying to fulfill is that we just oftentimes don't understand mechanisms for neuronal emulation, partly because a lot of these involve changes in atomic connectivity, electronic structure of materials, very far from equilibrium in response to electric fields and thermal gradients. And this is a problem, because if I go out and, of course, this is something silicon is very, very well understood. And then this is something that you can incorporate in all sorts of SPICE models and such, and that allows you to do forward and inverse design. If I build a solar cell, I understand the properties quite well, but incomplete understanding is a major challenge. And part of this is, again, we rely, or the field relies extensively on transformations, of transformations between two states or multiple internal states to get neuronal synaptic behavior. But it's often very hard to disentangle these and to independently tune these by structure composition, dopant density. So establishing these design rules would be really useful to get some sort of control. Really, again, this whole inverse design paradigm, coming down this chart that I show you on the right, into being able to correlate what you see for a device to fundamental properties of matter. And then another aspect of this that we've gotten recently interested in is how do you reconfigure nonlinear device? Could you sort of go back and forth between multiple transformations? And then ultimately, if you had your ideal material, and this is not an answer that I have today for you, but I think we're getting closer. What are the ultimate limits of energy consumption and processing speed ups that you could get as compared to digital computing in a stack for a fully sort of assembled structure? So those are some of the questions that we seek to answer, and really our goals at Remind are pretty much all about addressing these knowledge gaps and starting to design purpose-built materials that are meant for this. Remind has got 4 thrusts. So we've got a focus that actually Suhas Kumar is very actively involved in, and forward and inverse design, looking at device function, working backwards into material properties. And we've got 2 different classes of materials we've been interested in, intercalation materials, and they can be of different types. And again, Alec Pillen's got a big role at Sandia, amongst others, and then low entropy electrochemical transformations of coordination complexes, and then a tool building thrust, because part of what we realized as we were planning Remind, and we've been planning Remind for a while, is that there's a lot of missing information in terms of what exactly happens to materials, very far from equilibrium when they're transforming, when they're part of a neuronal or synaptic architecture. And one of the things that is distinctive to Remind, and I just want to sort of put it out there in case any of you all have any interest in this, is over the years, the PIs of Remind have built a very large foundry of molecules and crystals, and this is really this has a lot of opportunities for doing, it makes available very high quality materials for people looking to do things. And this, we hope that part of our sort of reason for existence is to sort of provide some benchmarking of materials across the field. And this is our kickoff meeting a few months ago. So that was fun. And I just want to say one more thing. So that's Remind, and we're really focused on the fundamental mechanisms and materials. We've got another thing that we've got cooking that we are waiting to hear from, which is a NSF SDC center, which is much bigger and really I think in some senses overlaps with COINFLIP, because we're trying to do this entire range from foundational mathematical frameworks, so coming up with theorems and guarantees, materials design, and then some demonstrator systems and co-design of algorithms. So that's something that's pending. It's a really large team of about 35 people. We haven't heard back yet, but we hope to soon, and we're excited about this possibility as well. Okay, so part of building neuromorphic materials is having a response that looks a little bit like this, right? Here, right. So something like that looks a little bit like this. This is what we've been trying to exploit for highly nonlinear dynamics, that dynamically tunable function that looks like a neuron, and then also to have some sort of reconfigurability, synaptic reconfigurability between two different ends. So a lot of this, at least our research, starts with some work that Stan Williams published about a decade ago, where he looked at niobium oxide and was able to really mimic a lot of different features of neuronal computing, probabilistic computing, including solving some of these global optimization problems. And he was able to distinguish some closely related sort of edge of chaos versus more periodic behavior that you could toggle between that. And the fundamental basis for this was the metal to insulator transformation of niobium oxide, which is at a very high temperature. And he was able to resolve integrated fire, pulse amplification, action potential, lot of these ideas. And this is sort of where a lot of our work comes from, is that we need to build this fundamental tool set of components, chaotic oscillators, amplifiers, some of them potentially much more powerful than transistors, right? And a bunch of nonlinear compute elements. And this will require understanding of intrinsic material properties and how to resolve them to build neurons, synapses, dendrites, and to then assemble them together. And if we can do it right, the hope is, of course, that we get to replace lots and lots of CMOS with interesting new devices that can perform interesting computations at low energies. And this is where we start. Can we identify the materials considerations that will allow us to get these sorts of thresholding, amplification, integration behavior, be able to control the volatility, for instance, and then understand how this couples with fields, and then come in and then break it down into spin, charge, orbital, lattice, atomic degrees of freedom in phase transforming materials. And this is a recent review on a material that has sort of occupied our attention for about a decade, which is vanadium dioxide. So what are we looking for at first glance? We care about a very nonlinear relationship, right? So not like a MOSFET, but something that is very, very nonlinear between voltage and current. Ideally, we would get this at very low input powers, to really move the needle. This is really necessary. And I think if you don't do this, there's a lot of heuristic designs based that involves very large material transformations that I think are destined not to succeed just because of how energy dissipative they are. And we'd like an operating temperature within the range of desired operation, very large endurance, and that's, easier said than done. Multiple internal states would be nice as well. And so as a material scientist and chemist, for this, a lot of this turns out to be how do we engender these very large electronic transitions, but with relatively minimal lattice distortions. So the material should not be changing a whole lot, but should be giving us very large variations in conductance, so we can get all of these information processing capabilities. And another thing that I sort of briefly mentioned at the beginning of my talk is how do we control these characteristics? If this is the characteristic we're trying to get, of course, a lot of the computing that happens depends on the steepness of onset, the volatility depends on the hysteresis, the conductance contrast determines the oscillations that are the stability of the oscillations. So how do we control these properties in materials? Part of this then for a material scientist turns into this problem of surfing these free energy landscapes, right? So if you imagine for a given composition, you got multiple axes that could be temperature, voltage, strain, whatever it is you want to call it, an external field, and there exist multiple local minima. How can you switch between two minima, each of which hopefully has a different conductance signature, through a relatively small barrier, right? That's our goal. That's what we want to be able to do. I mean, this is something, when I teach my undergrads about this, this is something that we see all the time, right? So polymorphs are common in chemistry and material science. So for graphite being the most thermodynamically stable phase, we have diamond as well, which is a metastable phase that has very interesting properties, of course, very different conductivity as well, right? Electronic conductivity. And of course, we're not going to toggle between diamond and graphite. That energy barrier is very large, but it's got the right set of characteristics in terms of conductance, right? If we could find materials with lower barriers, we could tunnel through or just hop across. So when we started this work in my group, at least about a decade ago, there's very few materials that have large change in conductance at reasonable temperatures, and I'll show you the landscape of that in a little bit. But VO2 is one of them. It at 67 degrees C, it goes from being an insulator to being a metal, and then you cool it back down, so you can get up to 4 or 5 orders of magnitude change in conductance. And in general, niobium oxide also gives you a pretty large change in conductance, but that's at 1100. Nickelates are important, VO2, and really what we've been trying to do is find so the mechanism for niobium dioxide is really this sort of linear chain dimerizing and undimerizing. It's very much a structural transformation, which is accompanied by a pretty substantial change in structure. In what we're trying to do is the other extreme of transformations, which is the Mott transformation, where you can drive these with relatively small changes in the structure, but through carrier injection and through essentially making changing the bandwidths of these. So this is either you inject sufficient carrier density so your electron-electron interactions can be overcome, or you facilitate better overlap between bands that either thermally or through some sort of strain that allows for a transformation into a metallic form. So we are trying to work in this end. So niobium oxide, very energy intensive, 6 femtojoules per spike, 1 femtojoule for VO2. Can we push this further? through more electronic transformations. That's our goal, right? So this is the landscape. A couple of years ago, Justin Andrews, who was my group, is just starting as an assistant professor at Purdue, put this together. Nature is not very kind. There's not a whole lot of materials inside close to room temperature. A lot of very low temperature materials, some high temperature. So this is our goal. I'll talk to you about maybe three mechanisms, and I will see how we get through all three, depending on the time. But like I said, vanadium dioxide is where we started. It's got a pretty interesting material that shows a sharp transformation, and we can make these materials, and if they're the right geometry, we can cycle them without cracking. So that's durability is important as well. And that's one of the challenges to having materials that have large structural transformations, is that they do develop fatigue because of the structural strain issues and such that happen. All right. So, of course, another thing that we'd like to do is really work at a bit higher temperature. 67 is still a bit low. We've played around with a bunch of dopants, or to be able to at least modulate the transformation temperature. So tungsten pushes it down, molybdenum pushes it down, niobium as well, germanium pushes it up. If you dope with elements like iridium, ruthenium, you get an entirely different polymorph, which is not very easily switchable. So part of what we've found out over the last decade or so is that this is a very rugged energy landscape, right? So there's a lot of different divots that you can sort of fall into here, and you want to get into the right ones, but not the ones that are sort of dead ends, and then to be able to identify parts of this landscape that you can toggle between. That's really been key. These are some levers that we have to really tune the transformation and sort of achieve our objective, like I talked about, of disentangling some of the attributes of the transformation, like the sharpness of this onset and such. So I saw a question from Shashank in the chat about, how important is it for it to be first order versus second order, and it's a really depends on what you're trying to do. For some of these oscillators, we've spent a lot of time getting very sharp transformations, very large conductance contrast, but there is such a thing as too much of an instability, because then you get an oscillation that becomes very hard to control. And so we have been tamping back a bit on the magnitude of the oscillation and the sharpness and such, because it just seems like you've got a bigger window to work with if you don't have such a sharp transformation. So a second, I don't know that we want to go all the way down to a second order, but a second order may not be terrible. Okay. This is an example of what dopants do to it, right? So moly and tungsten shift the transformation temperature down. Why is a good question. And so this is tungsten alloyed into vanadium. It turns out it generates a lot of anisotropic strain in the lattice. And so the large dopants cause strain. And so these severe local distortions really destabilize the monoclinic phase, and you can transform the rutile phase at a lower temperature. So in some senses, it's a little bit like the tungsten doping. And we've done a lot of local structure work that shows that around the dopant atom, there is a change in symmetry. It starts to look more like the high temperature phase. So tungsten really serves as this sort of Trojan horse, right, for nucleating this transformation. Another thing that we saw, the hysteresis, so the volatility is quite tunable by tungsten, and that's because tungsten alloying reduces the oxygen vacancy concentration and gives rise to this strained M2 phase that's in between M1 and R phases. So what happens is, because there's a strained phase that appears between an M1 and M2 and on R, you end up having very little of a barrier between for the heating transformation, for going up, or the forward transformation. It doesn't have to be heating, it could be driven by voltage or current as well. And so this forward transformation is driven, is nucleated at these phase boundaries. And so tungsten doping actually eases it as compared to undoped VO2. But on the way back, what happens is that you've got oxygen vacancies are really greatly reduced. And as a result of this, the reduced oxygen vacancy concentration, so you don't no longer have these phase boundaries in the high temperature phase. So at that point, the low temperature phase has to be nucleated through through point defects, and the point defects being reduced upon tungsten doping, you end up supercooling the transformation. So tungsten doping provides a kinetic, eases the forward transformation and hinders the reverse transformation, which provides a mechanism for imbuing volatility or non-volatility into the system, so having a larger hysteresis. We played around with another, we wanted to push it higher, and we have actually now pushed it up to about 85, 90 degrees C through germanium alloying. And it turns out that germanium alloying also suppresses the oxygen vacancy formation. And if you do it under oxygen-rich conditions, you almost really kill the oxygen vacancies. And at that point, you get a very, very large hysteresis. So that's something that is also interesting. But whereas if you do it under oxygen-poor conditions, you still get enough oxygen vacancy concentration that you don't get as much of a hysteresis. So this is a approach that is also interesting for us, because this, for the first time, allowed us to disentangle the transformation temperature and hysteresis, right? So germanium pushes the transformation temperature up, and then depending on your oxygen vacancy concentration, you can have more or less hysteresis. And then the oxygen potential is something you can dynamically control as well through, for instance, ionic liquid gating or something like that. You can sort of take it back and forth between these two extremes with high or low volatility. And the reason, again, the germanium does this is it sort of enforces greater pairing of these dimers in VO2, so that increases the temperature required. So it stabilizes the M1 phase as compared to the R phase. And so another material, another very different doping that we've done is that has shown us some really intriguing behavior, is to put boron in. And boron is, so germanium and tungsten sit on vanadium sites. Boron is a bit too small for that, so it actually occupies these interstitial sites. And there's a bunch of interstitial sites inside VO2 that it can occupy. And in the two phases of VO2, the low temperature monoclinic versus high temperature rutile, it turns out that boron has entirely different preferences. So the way we put boron in is sort of this rapid thermal annealing after putting a precursor on. And so what we interestingly are able to see is that after you cool down boron doped VO2, the forward transformation temperature depends on how long the material's been sitting around, right? So you could have something that's unrelaxed, intermediate, fully relaxed. And so this is a hourglass, and it's, I mean, completely reproducible every time, almost a fundamental constant. The transition temperature depends sensitively on how long the material, since the material was cooled down, and the temperature history. Okay, those two things. And so you can see this here as well. If I run this here, this is, and then I cool it back down through this is the fully relaxed, and then I go right back up again. It transforms at a very, very different temperature. And this is, you can see this in thermally driven transformations, voltage driven, current driven, and as a function of temperature versus time, we can plot this out. This is what it looks like. The transformation, the forward transformation temperature is extremely nonlinear, and the reason that we see this again is that boron, it turns out, and it took us a lot of time to figure this out. Boron, in the high temperature state, boron sits in a has its favorite side, which when you quench it to lower temperature, when you cool it down, it gets stuck in its symmetry equivalent side in the monoclinic phase. that symmetry equivalent side is a 3-coordinated trigonal planar side. It's not the most favored side in the low temperature phase. And so then boron starts this journey trying to get into its low temperature, its lowest energy site. And we have spectroscopic signatures of each of these sites in boron zanes. And as it starts this journey from one side to the other, the transformation temperature keeps evolving. And so this is both a clock and a thermometer, depending on how long it's been sitting around and what temperature. And the transition temperature encodes the time and temperature. So this provides, we're excited about this. This is getting into a little bit more transports because it's got multiple internal states as these domains switch over. And with the current driven transformation, you can really get analog behavior here across multiple states, and you can imbue this time dependent response that is it's slow, so way slower than probably of interest, but this is a mechanism through which you can control this. So this is sort of some of what we've been playing with in this idea in the VO2 space. Extremely rugged and complex landscape. If you dope it with some elements, you just completely put the structure out of play. Tungsten allows us to reduce the transformation temperature, and germanium increases the transformation temperature, allows us independent control over hysteresis. And then boron is a diffusive dopant that really gives us some interesting dynamics of the transformation that are encoded inside the material property. So it's sort of an intrinsically memoristic material, right? All right, and then that's a whole other interesting set of material. But and we, some of these doping can help reduce the structural part of the transformation, focusing a bit on the electronic, or trying to get it more electronic. So slightly different story. So we and this is something that we probably have really pushed the needle the most on is going beyond VO2. So alloying VO2 is one, but can we fundamentally find new materials that have these transformations? As I showed you in that atlas, there's very, very few that are in this regime. So we've started to implement several of the design ideas from VO2. This is a V2O5 crystal, which has copper inserted in it, and it shows beautiful transformations all the way from 150 to 390 Kelvin, depending on what that transformation, what that stoichiometry for copper is. We could get voltage-driven transformations and current-driven transformations, and build oscillators out of these. And of course, the oscillations depend on not just on the material, but also what's around it, what's the resistance, and what's the circuit. And so this seemed like a great material to really try to understand mechanisms, and this is what it looks like. It's got this a one-dimensional V2O5 framework, copper ions arrayed in the tunnel, and we saw that across the transformation, the volume expansion across a whole 300 Kelvin range is less than 1%, right? So very, very little change in the structure, which is amazing. We don't want to have large changes in structure. Along the B-axis, the lattice does contract, which is what seems to underpin this transformation from a insulator to a metal, but it's only by 0.04%. So again, really pushing the limits of what we could do for structure here. And then what is amazing about this, because these materials are so robust, if I take a large chunk of VO2 and I try to heat it back and forth between conductive and insulating states, it cracks almost immediately. But because these materials are so stable, I can take a large single crystal and sort of heat it and cool it through this transformation temperature. And I see at low temperatures some very localized electron density for copper, and then high temperature it spreads out, and this is a different stoichiometry. So essentially, the core mechanism, and in this case we can actually do single crystal diffraction to identify it, is that you have localized copper. So copper sits between one side or the other side, And as it sits in one side, one of the vanadium atoms here is selectively reduced, okay? But then as you increase temperature, it's not just one vanadium atom, but it's adjacent one as the copper shuttles, the electron density shuttles as well. So we go from having very localized electron density to very delocalized electron density. And that's what in angle resolved photo emission, you see this energy band gap close at high temperatures. And it's because these copper 3D states introduce these states in the middle of the band gap that allows for these states. So depending on the copper vanadium oxygen vanadium hybridization, you see this this open up and close. So in other words, what is actually going on is we see this change in copper occupancy at different sites. And what is exactly going on is this shuttling of copper ions. Let me see if I can play this movie. It's this movie plays. Okay, there we go. All right. So very little shuttling of copper ions that causes the electrons to not be localized on one vanadium, but to slosh around between two adjacent vanadium and delocalizes the electron density. But all of this is happening with, so you get this big transformation in the electronic structure. All of this is happening between these split sides with very little structural change, right? Which is ideal for getting a low energy transformation. So hopping of copper ions melts this polaron, and with sufficient mobility, conduction is activated along the whole tunnel. And now, depending on how much copper we have in the tunnel, if you've got a lot, it doesn't take very much to have this all turn conducting very soon. If we have relatively little, then for the conducting channels to form requires a little bit more temperature. So that provides a knob for tuning the temperature and or threshold voltage at which this transformation happens. We've been playing around with this, again, trying to get some mechanisms and understand mechanisms and such. Is we have another structure, but we said, well, since copper in V2O5 is good, but can we, instead of this tunnel structure, can we take a 2D layered structure and would that work? And it turns out it does. It's a little bit different in mechanism. This is again 150 Kelvin. This doesn't actually change very much, depending on the amount of copper. And the mechanism for this is that at low temperature, the copper ions are arranged in a supercell. So they sort of really stack in a very ordered manner. And as you increase temperature, they disorder, and then the disordered state has a lower conductivity. And so you can see that here, the superlattice reflections are gone with increasing temperature, and that temperature with superlattice reflections are gone coincides pretty much exactly with this temperature for the structure, the transformation. So we've done a bunch of ab initio molecular dynamics simulations. It looks like this is how the copper ions are arrayed at low temperature, 110 Kelvin, and then as you increase temperature, they actually start to move along this pathway to reorder, which has been really fun to see and to really be able to model what we see in X-ray diffraction by first principles simulation. So you can see that really move across the entire range, and that and the energy barriers for this are very small. This is again key. Not the layers are not moving. There's a little bit of copper shuttling going on between the layers that drives this change in conductance that we can use for as a nonlinear dynamical sort of switch. And we've got a lot of levers available, and I think this is why the case we make is we are the group that can identify some design principles, because you saw layered structures, but we can really we have a whole library of compounds that we can make For instance, we can start with alpha V2O5, we can lithiate it, we can take this out, and we can get this puckered layered compound that we can stuff with ions like copper or something else. This is the original layered structure of data V2O5 that I showed you, where we can take copper, and this is this double layered epsilon prime, which is the latest work that we haven't published yet. And the other thing that I want to talk about at the probably the last few minutes, and so a lot of this is like playing Jenga, right? So we take these compounds, we pull ions out, and we put other ions in. We can get these ions to move, and so by doing so, we can trigger these transformations that are precisely tunable, and really there's just a humongous amount of flexibility in picking what the Jenga blocks look like and what goes inside, and that we're hoping will give us interesting materials, but also design principles for exactly how to tune it. So this is an example that we just published a few days ago in Matter, and this is that data structure that I showed you where copper does this little jig and uses so we identified, because again we've got very high resolution X-ray data. We identified 4 different sites where we could potentially put ions in, and then Joe Handy in my group went ahead and selectively put lithium ions at each of the sites by blocking other ions. So for instance, if he takes silver and he blocks the silver sites, the beta sites, which are these 7 coordinated sites, then the lithium goes into a beta prime. If he takes copper, which occupies the beta site, then the lithium goes into the beta site instead. If he blocks the entire beta prime site, then the lithium goes into this I site right in the middle. And if he blocks the entire tunnel, then it goes outside the tunnel. So the idea being that we can do site selective modification and precisely tune the compounds we make and have them, have our electron density be very carefully situated in these states, and of course they show very distinctive signatures by lithium NMR and by resonant inelastic X-ray scattering. So this just got published. So what this is supposed to show is this, right? So Babe Ruth calling his shots, and so positioning ions where you want it. That's the analogy here, in case you're wondering why there's a baseball player on the cover of this respected scientific journal. But well, the editor went with it. Okay, so just to end here and leave time for questions. I think what I've tried to show you is that what I've hopefully tried to motivate is the need for coming up with interesting new materials that have a lot of nonlinear dynamic transformations embedded in them, which would make, I think, a lot of device design a lot more easier. And the properties of these materials will hopefully inspire a lot of folks like in COINFLIPS to come up with new architectures and new ways of computing. And I think that's our hope. Again, we are, as an EFRC, very focused on mechanisms and materials, but we're really hoping that these discoveries that we make will inspire greater collaboration, at higher levels of the stack. So thank you, and happy to take any questions.
Awesome, thank you so much. Yeah, so audience, feel free to post questions in the chat and I can read them out loud, or if you prefer, you can unmute and ask them yourself.